Class 15. Welcome to Class 15. Not sure when that thing started. We're going to do some more examples of steady state processes. And yeah, I think that's what this class is about. I think we're also going to do some mixing, right, which is also a steady state process. So yes, it does count. Let's see. So this is the first example. It's going to deal with a pump and this tank. I think this is still a steady state process. Sure. The other things we're going to cover in the subsequent videos, we'll do this example, which is a complete cycle of a power plant with a turbine, a complete cycle with a refrigerator with a compressor, and we'll do this mixing chamber, another heat exchanger, another mixing thing going on here, and another mixing thing, and another heat exchanger. So those are our plans. So let's start out with this one and this for this video. All right, so boom, let's go to there. All right, so read the problem. Small liquid pump, this guy right here, is located 15 meters below the surface of here in a well. I guess he's down below the surface of what I mean by that. Taking water in at 10 degrees Celsius and 90 kilopascals at a rate of 1.5 kilograms per second. The exit line is a pipe diameter of 0.04 meters or 40 millimeters that goes up to a receiver tank, this guy, maintaining a gauge pressure of 400 kilopascals. Assume that the process is adiabatic. That means no heat is getting lost, with the same inlet and exit velocities. That means the pipe diameter is the same, but well, no, not necessarily. Okay, because it depends. It depends. All right. So it depends on the specific volume, right? So the mass flow is the same in and out. So if the specific volume were to change, it might have a different volumetric flow. So it might have a different diameter. But they said the diameter for one of them. I'm sorry. Anyway, the water stays at 10 degrees Celsius all the time. So maybe I'll take that back, and it's probably going to be the same. In any case, we need to write out maybe our big equation. Our big equation for conservation of energy is going to be 0 is equal to Q dot minus W dot plus the summation of M dot, and we're going to go enthalpy in plus inlet velocity plus squared, right? So this is the kinetic energy per mass, but we're multiplying it by M dot right there. GZ in minus the summation of M dots crossing, and I guess maybe that should be MI, and this should be ME. HE plus VE squared over 2, right? So there's the kinetic energy plus GZE. Right, and these are represent the potential energy, and we're going to go ahead and treat this one like 0 because we're going to say this is the 0. We often will call that the datum. See, that's where we're referencing the bottom of it too. These are going to be cancel each other out actually because they have the same velocities in and out. I think we're okay right here. We're going to be putting work in, so do I want to do that right now? I guess so. We'll put that in as negative power in, right? And it's adiabatic, so that's 0. All right, so I think I got all this. There is something that we should know, and that is for pumps, and this is particular to pumps, that the total enthalpy, the enthalpy coming out here, is going to be a combination. So I'll write this for pumps. This is like a piece of information we don't have yet, so I didn't know how to convey it. We have HI plus the exit pressure minus the inlet pressure times the specific volume. Hopefully that remains the same, right? It's not going to work out very well if that doesn't remain the same. So that's going to come in and play a part. And you note that this already has an HI, so it's going to cancel that part out. So just be aware of that. I'm going to get some of the, I think I can go ahead and proceed. With all this stuff that we're left here, we're going to take this power and stick it onto the left-hand side of this equation. Because that's what we want to find, right? We want to find the required pump work. They say pump work, I think pump power. Okay, so what we're left with right here, we have the same m dot in and out, so we didn't need to necessarily make these different, but there could be different masses coming in and out of this system. So that's well and good. So what we're going to end up with is, you notice I had that minus here, but this guy jumped over to the other side. So we ended up getting GZE. That's going to be the fact that this thing has gone up 15 meters. They call that pump head, by the way, when you're increasing the height of something. You'll learn about that in fluid mechanics. And this right here, it should be a positive value. Oh yeah, because this negative right here. Okay, so this HI actually gets rid of this, and what we're left with here is a PE minus PI and specific volume. I think that all works out right here. So that guy went over to here. This guy got killed by that. And this got in there. Okay, so this is what we have left. So we were told the mass flow. Sure, we were 1.5 kilograms per second. We have G, which is 9.81, times Z, which is 15. Now you're going to have to divide this by 1,000, because all these other things are usually going to be done on a kilojoules per kilogram inside here. And this right here is going to be meters squared per second squared. And as we talked about in the previous video, if you work through that right there, you have to divide this by 1,000 to get them to work out. Here you're going to go plus, and we're going to go kilopascals. And something we should have paid attention to up above when we read this was they said gauge pressure of this, right? So that's the exit pressure up here, right? So that's a gauge. So in order to compare it to this one right here, which we're going to assume is absolute pressure, we have to take and go 400 plus 101. You can put 101.3 if you want into there. It doesn't matter. It won't make that much of a difference. And then we subtract PI of 90. Multiply that by the specific volume. I'm going to go ahead and use the estimate for water. Pretty basic. This is the 0.001 cubic meters per kilogram. It's the same thing, saying the density is 1,000 kilograms per cubic meter, and it's usually pretty much the same thing. And we'll work through all this right here. We're going to get a pump power of 0.8372. These are kilowatts because we would have gotten kilojoules per second. I think you're better off if you have something as a fraction. Go ahead and get it as watts. And that's enough for this example. And I'll make next videos be the next example.